But by results of set theory, we know that whenever A is subset of B and B is subset of A, we have A is equal to B. It means whenever A is related to B and B is related to A, we have A is equal to B. This means this relation is antisymmetric. And next one is subset or equal is transitive. This is also obvious. Let we have three sets A, B, C in Px such that A is related to B and B is related to C. So by definition of this relation, we have A is subset of B and B is subset of C. So by results of set theory, whenever A is subset of B and B is subset of C, we have A is subset of C. It means A is related to C. Thus, whenever we have A is related to B, B is related to C, we have A is related to C. It means this relation, subset or equal, is transitive on this set Px. Thus, this relation is reflexive, antisymmetric, and transitive on Px, and therefore Px together with this relation is a poset. Next one is let n be a natural number and Sn is equal to this set of all m in n such that m divides n, and define for mn belongs to Sn m dn, that is m divides n. It means we have this relation. We have this set Sn is equal to m in n such that m divides n, and we have this relation less or equal defined by this m1 is less or equal m2 if and only if m1 divides m2, and we will use d also, so m1 d m2. So in this example, it is clear that if we have a number m1 in Sn, then m1 divides itself, means we have this m1 divides m1. This is obvious, so, and this is true for all m1 in Sn. It means this relation is reflexive. There is nothing to prove. Next one is, suppose for the anti-symmetricity, suppose m1 divides m2 and m2 divides m1, both are in Sn. Then by the results of number theory, we can say that this imply m1 is equal to m2, means this relation is antisymmetric. And for the transitivity, suppose m1 divides m2 and m2 divides m3, then again by results of number theory we can say that m1 divides m3. It means whenever m1 is related to m2 and m2 is related to m2 is related to m3, we have m1 is related to m3. It means this relation division is also transitive. So division is reflexive, antisymmetric, and transitive. So on this set Sn with this relation D is a poset. From this, my colleague Professor Rajesh Ram will continue from here.
Thank you. Now we are going to see the concept of lattice, and for that we are going to see some certain essential topics for understanding lattice, and for that we are going to consider cover of an element in lattice. Cover of an element, we can see this cover of an element. We can see, let us consider any poset. We will have already seen in previous session, P together with the relation less or equal is a poset, and consider a member A from P, B is another member from P. If A is related to B, and there is no any Z, there is no any Z in P such that A related Z and Z related B, then we can say that B is a cover of A. B is said to be cover of A. For that we are going to see one example of cover. We are going to consider one example by taking S12. Consider S12. S12 means the factors of 12. Consider S12. 1, 2, 3, 4, 6 and 12. These are the factors of 12, and the relation we are going to consider, that is D. Relation is D. We can see here the 2 and 3 that covers 1. Why? Because 1 is a divisor of 2, 1 is a divisor of 3, such that there is no any Z in S12 such that 1 related Z and Z related 2. Similarly, there is no any Z in S12 such that 1 related Z and Z related 3, so that 2 and 3 are the covers of 1. Similarly, let us check about 4. Is it true that 4 is a cover of 1? No. Why? Because there is 2 in S12 such that 1 is a divisor of 2 and 2 is a divisor of 4, so that 4 is not a cover of 1. Similar fashion, 12 is also not a cover of 1, 6 is also not a cover of 1. Now we can consider the case of 2 and 3. Now we can see that 2 is not the divisor of 3, so 3 cannot be a cover of 2. Similarly, let us check about 4. So it is very clear that 4 is the cover of 2. Similarly, 6 is also cover of 2. So in this sense we can see the covers. Similar fashion, you can also see 12 is the cover of 4 as well as 6. So that is about cover. Now we are going to see the next article. It is the upper and lower bound. Let us consider any poset P. We are going to consider P is a poset together with the relation less or equal. Less or equal is a partial order relation on a set P, and suppose A is any non-empty subset of P. P together with the relation less or equal is a poset. And what is A? A is any subset of P. A is a subset of P. Now we are going to see the lower bound and upper bound. For that we consider an element X from P. X is any member taken from P. If X is lower bound of A, it means that X is related with each and every member of A. Then X is called lower bound of A. Similar fashion, if there is X in P such that all A belongs to A are related with X, then X is called an upper bound of A. We can consider so many upper bounds in the poset. Let us consider two upper bounds or two lower bounds. For example, we consider two lower bounds. Let us consider x and y are any two lower bounds. And suppose that x is any fixed lower bound and y is any other lower bound. Least upper bound means that it is a lower bound which is least to all the lower bound. We can see by the definition that x is the lower bound which is said to be greatest if all other lower bounds are related with the x, then x is called the greatest lower bound of A. Yes. Similar fashion, we can consider the least upper bound. For example, x is any upper bound of A and x is related with y for all upper bounds y of A. Then x is called the least upper bound of A. We are going to see one examples of that. We will have already seen in previous session S12. S12 is nothing but the set of all the factors of 12. 1, 2, 3, 4, 6 and 12. These are the factors of 12. We can see the relation less or equal is D. Means that if A is a divisor of B, then A is related to B. So that we will have the different members in S12. Look at here 1. 1 is a divisor of all the members of S12. So we can say the greatest lower bound of S12, it is to be 1. Similar fashion, you can see the 1, 2, 3, 4 and 6. These are all divisor of 12. So that the least upper bound of S12, it is to be 12. Similarly, we can consider the another examples also. And now we are going to see our main point, what is lattice. Now first of all, we are going to see lattice as a poset. We are going to consider the poset. Now we are going to use the notation L for that. We can consider L together with the relation less or equal is any poset. Suppose that it is any poset. Now when we say it is a lattice, we can consider whatever x and y from L, if the greatest lower bound means GLB of x and y exist and if it is a member of L. Similarly, the least upper bound of any two members x and y, it is in L, then we can say that L is a lattice. We can see that things through some certain examples. We are going to consider one simple example, that is S6 means set of all the factors of 6. These are 1, 2, 3 and 6. These 4 elements are there in S6. So now we are going to check about the least upper bounds and greatest lower bounds of pairs of two members. For example, we consider 1 and 2 and we are going to examine the greatest lower bound of 1 and 2. It means that GLB of 1 and 2, it is defined as the GCD of 1 and 2. GCD of 1 and 2. GCD, greatest common divisor of 1 and 2. What is that? You can see it is you can find it. Similar fashion, you can consider the greatest lower bound of any two members also. For example, 2 and 3. 2 and 3, 3 and 6, 1 and 3. Similarly, 2 and 6, 3 and 6, etc. You can see that all these greatest lower bounds are members of S6. So that all any two members, let us consider x and y from S6. It is very clear that the greatest lower bound and least upper bounds that are contained in S6. So we can say the S6 is together with the relation less or equal means divisor, it is a poset. That we can see. Similar fashion, we consider one another example. The set of natural numbers n together with the relation less or equal, where we are going to consider less or equals is the divisor relation. If A is a divisor of B, then and only then A is related to B. So we can see it is also lattice by elementary inspection. For example, we consider any two members M and N from N. If M is a divisor of N, then M is related to N, and you can check the, let us consider any two natural numbers. You must find the greatest lower bound and least upper bounds and check whether that are also in N, so that N together with the relation less or equal is again a lattice. Similarly, we are going to see one another point, that is the meet and join. Meet and join of two members of lattice. Now first of all, we are going to see the meet and join. Let's consider two members from lattice. For example, A and B are any two members taken from any lattice L. If we are going to define A star B, that is the greatest lower bound of A and B, and if we define A ring sum B, that is the least upper bound of A and B, then that star is called the meet of A and B, and that the relation, that the operation ring sum is called join of A and B. Similarly, from the definition of meet, it is obvious that the A star B is the greatest lower bound of A and B. So any other lower bound should be less or equal the greatest lower bound. And similar fashion, least upper bound, it should be the least than the all upper bounds. So from the definition, it is clear that A star B is always related to A. Similarly, A star B is also related to B. Similar fashion, by the definition of ring sum, we can see that the ring sum